Hello, my name is Mr. Shower, and I'm going to share with you in this screencast what we normally do as a lunchtime or early morning seminar to help you figure out what statistics is and why you need to do it with your ISEF project. So let me go ahead and walk you through a little bit about statistics in general, and then we'll get to specifically how that might tie into the research project that you are in the process conducting and getting data for. So the field of statistics is all about data. It's how you collect data in an appropriate manner, and your research plan would have hopefully been set up in such a way that you're collecting data that answers the question or attempts to answer the question that you are hoping to explore. And so that involves taking into account variables that might affect your data, controlling for what might influence it that you really don't want to have influence it, getting an appropriate sample size, but it involves what is the best way to collect data that is going to answer the question that you want to ask, right? Once you have that data, you actually have to be able to describe it. So you don't want to just plunk down a large table full of numbers. You need to find ways that you can describe the data that you've collected so that somebody looking at it can quickly get an idea of what it was you found. Once you have that description, then what you're trying to do is figure out what are the trends that are going on in my data, right? And generally, those trends are trying to answer the question. So you might be looking for a difference between or among some different types of samples. You might be looking for a relationship between one or two variables. Or you might be looking for something that happened more or less than you expected it to happen just by chance. So that's a big part of the statistics. And you can only analyze those trends if you, back in the beginning, set it up in such a way that the data that you collected was intended to analyze those trends. Once you have those trends, then you are going to infer what those things are telling you. As you'll see, there's several major branches of statistics, but you're going to know exactly what was going on with the sample that you collected. What you may not know, or what you're going to try to do, is infer what that sample is telling you about the world as a whole, right? Uh, so anyway, that is kind of the goal of statistics. And the other piece of this is how in the world do you communicate all this statistical knowledge to your audience, whether that audience happens to be a friend, a family member, or a judge that's deciding whether you win your category or not. Right? So I want to break it down into two major areas of statistics. There's the descriptive area, and there's the inferential area. So those of you that end up taking AP statistics, the first part of the class is usually dealt with describing statistics, descriptive, and then you get into the inferential part. So when we're describing statistics, you need to do things where you are presenting your information in a concise, usable, and understandable form. So again, that's organizing data tables into summary tables or into appropriate graphs for your data. Or in some cases, it may be pictures of things that you are finding in your results, right? So it's very important that when you do this, you choose the right kind of charts or graphs or tables for that data. Oftentimes we have people that will do scatter plots, an X versus a Y, and because they've been trained since childhood, they want to connect the dots, but there might not be any connection of the dots. So line graphs where you're connecting dots, like you can see in the lower corner here, are things where you actually have time series data where you are getting from one point to the next. So you do connect them in a line, right? Oftentimes, though, what we're doing is we're generating scatter plots of points that represent two values of two different variables. And in those cases, we're not connecting them. We're trying to plot a line that fits those data best, a line of best fit, which is another type of statistical description, which can turn into a statistical analysis, right? So you do have to be careful. A lot of times what you're trying to do is summarize things about data, like its shape. Is it uniform? Does it have the same kind of values all the way across? Is it bell-shaped? Is it nearly normal where it's really peaked in the middle and tails out on the ends? Is it skewed one way or another where there's some data on one end but not much on the other, and vice versa? Is it bimodal? You have a bunch of low values and a bunch of high values. So there's ways to describe the shape of your data if it is data that is based on quantitative values. You would not describe data, the shape, if it's something that's based on categorical values or qualitative values. Likewise, you want to describe the center, the mean. Sometimes median is actually better than mean, and you can take a look at how you might describe either of those. Most times you actually try to describe both of them. And then we also talk about spread in data. When we're working with quantitative data, we want to know, is our data really spread out relative to the mean, or is it really concentrated relative to the mean? That's where a measurement called standard deviation comes in. You can also do things like describing range. One of the things, though, is these kinds of descriptions work on quantitative data, data where you're working with numbers that you've measured, or in some cases, numbers that you've counted. But you wouldn't really do those kinds of things with categorical data. You do things differently with those. Categorical data, you might do things like bar charts or pie charts that are showing you how much are in a particular category. But I do want to point out something about this graphic down in the corner. It looks pretty, but it is bad, very bad, right? So one of the things, there are lots of graphing tools out there. There are lots of bad graphing tools out there. The 3D pie chart is, as some of my former students know, one of my many pet peeves. But the reason you don't want to use a 3D pie chart is when you tilt it on its angle, you lose the proportions that a pie is intended to show in the first place. The bar graph, the 3D bar graph on the other side, is less problematic because all of the bars have the same footprint, right? So they're all the same volume and they still stay high relative to each other, but you still even there run into some problems with perspective. But in the case of a pie, sometimes it's actually intentionally used to be a bit misleading. When you tilt it on its side, sometimes the slices of pie that are in front look bigger than the ones that are in back simply because they happen to be closer. Don't use 3D graphs most of the time, right? And especially not 3D pies. But graphs are a way that you can actually describe your data that gives you a very quick, or gives the reader, your audience, a very quick idea of what your data looks like and what kind of patterns it might be taking on, right? So describing data or giving some summaries of it, giving some appropriate pictures of what the data looks like. And that's where historically a lot of people stop in their projects, and you don't want to stop, right? Because all that does is tell you what you have for your sample. What you want to do with that is help tell people what your sample data is telling you about the real world, right? So what we're trying to get you to the point of is what are called inferential statistics, right? In inferential statistics, we are using sample data to infer something about the population that the sample happened to be taken from, right? If I do a sample of students, I can infer something about the population that those students were drawn from, as long as I collected my data appropriately, right? Now, when we talk about, are these differences or relationships real? It's like, what do you mean they're not real? We collected them from the group, right? But when we're doing samples, we would often expect to find a little bit of variability from what the population was that we drew that sample from. I'm going to give you an example here in just a minute, right? So when we do statistical analysis, when we try to find something that is statistically significant, what it's telling us is that the values that we got really are something that's going on as opposed to something that's just based on random chance, right? So it is critical that you do this, otherwise you really haven't answered your question, right? So again, you're designing a study that's going to collect data by using a sample. We can describe the data from that sample, and then we can take it to the next step to infer what that sample data is telling us about the real world or the population that we happen to be interested that we sampled from. And it's going to do that by generating something called a p-value, right? So what is a p-value? I describe it as the punchline of inferential statistics. Any kind of statistical test or statistical analysis you do is going to give you a p-value. And if the graph on the left looks kind of as scary, intimidating, don't worry about it for now. We're going to come back to it in just a minute. But what a p-value does, it describes the probability that you would get the sample data that you collected if there really was no difference in the population that you drew it from, right? Or if nothing's going on, or there's no relationship between X and Y, or what you were observing is no different than what you'd expect, right? So here's a more simple way and concrete way to think about that. Let's picture flipping a coin, right? Is the coin fair, right? So, well, if we had a suspicion that a coin was not fair, we could flip it a bunch, right? And one of the things we would want to do is figure out how much we need to flip it, right? There's ways to get about that. Hopefully you have a big sample size. And that sample size, the bigger the sample size, the easier it is to detect the differences that you happen to be looking for. All right, so let's do an example here. All right, so let's say we've got a coin and we're pondering whether the coin is actually fair. If it's fair, we should get about 50 heads when we flip it 100 times. We actually really don't expect to get exactly 50 heads every time we flip it, but we should be somewhere close. So I flip the coin 100 times and I get 52 heads. If I ran a statistical test on that, the probability that I would get at least 52 heads, right? Not exactly, right? But the probability that I get 52 heads or more, or something that extreme, has a p-value of 0.34, 34% chance of happening, which just isn't all that unusual, right? So there's a 30% chance I'd get us that far away from 50%. Not too unusual. We got 50 heads, we'd expect, but there's a 34% chance of getting 52 or more heads out of 100 tosses. I'm pretty sure that coin's not unfair, right? I don't have very good evidence that it's different from 50%. If I flip it 100 times and I get 60 heads, well, that would make me maybe a little more suspicious. I run the same test. Probability that I get greater than 60 heads, assuming the coin's fair, is only 2%. Now, that's what we would consider statistically unusual, right? So there's a very low chance of flipping 60 heads out of 100 toss if we assume we have a fair coin. Therefore, there's strong evidence to reject the hypothesis that the coin is fair. So some of this wording would be, what do we think is happening? Well, we think it's different. So we're going to actually test against it not being different, that there's really nothing going on, right? So let's go back to that curve, right? This most likely observation for a coin, if it's fair, is 50%. My 52 heads was down here somewhere. So that still got a pretty high chance of happening. Now when I get out to 60 heads, I'm starting to get down out in this end. And what I'm going to say is, yes, it is possible, but there's only a 2% chance of it happening if it's really 50%. And so I say I have pretty strong evidence that it's not 50%. This is getting in just a few minutes presentation what we generally take weeks to do in an AP statistics class. So if you're getting a little confused, that's not a surprise. If it's starting to go, oh, I'm starting to get it, that's kind of the goal. So for this year for ISEF, we will be doing statistics consulting as students start getting data. I'll be available by appointment. You can email me and we'll set up times. The goal would be to have a conversation with you to help you figure out what are the appropriate graphics, what is the appropriate analysis, and once you have that, how do you communicate your findings, right? So how do you communicate your findings in text and voice, and potentially via Zoom with a judge. All right. So there'll be some appointment information coming later this fall. I apologize for the pauses, kind of doing this on the fly, and I hope you found this helpful. And again, email me if you are ready to get some help with your data. And thanks for paying attention.